Okay, what if you have something other than a gas? Because there's lots of things that have solids or liquids, right? Well, because the concentration of a solid or a pure liquid doesn't change, any species that's labeled solid or liquid, S or L, is not included in the equilibrium expression. So this is called a heterogeneous equilibrium. And the example here is carbon. Well, here, looking at this equilibrium, you have carbon monoxide in equilibrium with carbon dioxide and solid carbon. So if we were to write an equilibrium constant for that, we would start out with, let's just do it in concentration. It's the concentration of CO2 times the concentration of solid carbon divided by the concentration of carbon monoxide squared. But how do we measure the concentration of a pure solid? Well, we can calculate the molarity of a pure solid or a pure liquid. The molarity of pure water is like 55 moles per liter. But does the concentration of this carbon change if I have a lot of it or a little bit? No, it doesn't. Because it's the same number of moles per unit volume. It's related to the density, right? The density doesn't change, the molar mass doesn't change, and so the concentration of the solid doesn't change. So this term for the solid has no effect on the equilibrium. So we leave it out. Because if we look at the equilibrium in these under these two, these look like cake jars, or cake covers, we would find that we would have the same concentration of CO2 and CO, regardless of how much carbon was sitting in the bottom. As long as there is a little bit present, it doesn't matter at all. Anybody have any questions about that? So let's write the equilibrium expression for the reaction between carbon dioxide and water. So we've got our chemical equation there, and there aren't any coefficients. Personally, anytime there's no coefficient, I always double check that I'm not being handed an unbalanced equation, right? So 1 carbon and 3 oxygen, yeah, it's balanced. So they want the equilibrium expression, so K is equal to the concentration of the products. So we've got hydrogen ion, and we've got hydrogen carbonate ion divided by carbon dioxide. And am I going to put the concentration of water in there? No, because it's a pure liquid. It's an L, so we're going to leave it out because it doesn't change and it doesn't affect the equilibrium. Questions?
Is it just K or is it KC?
Well, the way I've written it here with the brackets, it's KC. KP wouldn't work for this one because I have some aqueous things and they don't have pressures. If it was all gases in a solid, we could do KP or KC. Here's another one. Write an expression for the equilibrium constant Kc, it specifies, for this chemical equation. What does this end up being? Just the concentration of CO2. Yes.
If it had coefficients, it'd be exponent.
Yes. Yeah, if there was a coefficient of 2 in front of CO2, then this would be squared. Yeah.
Say this were reversed, so it was CO2 gas plus CaO solid to CaO solid to liquid solid. Would it then be Kc equals 1 over
Mm-hmm.
CO2?
Yep. So looking at the reverse reaction, Kc equals the concentration of the products, but there's only a solid, divided by the concentration of reactants, CO2, but we can't have nothing up there. It's 1 divided by. And that goes along with the rules of manipulating equations. When we reverse the direction of the equation, we take the equilibrium constant and invert it. So this equilibrium constant and this one are inverses of each other. You upside down it. Any other questions? Right, the equilibrium constant for this one. Give you a minute to do it yourself. So what's in the numerator?
H2O. Oh, my bad.
And in the denominator, I've got the HCl to what power? 4th power, and O2, the 1st power. Leaving solids and liquids out is rather disturbing to some people. I get that. If you want to talk about it after class, we could set up a group counseling session.
Oh my God. We got just over a wire right now.
Well, everybody's a little stressed out from the exam, right? So we just don't want to push anybody over the edge.
Did you say what the equilibrium constant is like its purpose?
I did, but you've been studying for the previous chapter, so it kind of got pushed aside. The equilibrium constant tells us if the equilibrium favors the products or the reactants.
That's right.
Yeah. It tells us how far the reaction
So
goes.
the bigger the constant, the more favor it is for forward.
Yes.
And the smaller is
So a small equilibrium constant means the reaction does not proceed very far at all. You're not going to get much product. A large one says it's going to go way over to the products. There'll be very little reactant left. So you can imagine that if you're manufacturing something that depends on some chemical equations, some chemical reactions, then you're going to care about your equilibrium constants because they're going to affect your yield. Because in Chem 1A, we assumed that all the reactions went 100%, but they don't.
So if the equilibrium constant in the last example, or no, maybe it was the one where it was just, this one.
This one, just CO2?
So if it's only dependent on CO2, how does that affect a reaction? Like with that knowledge, how would you go to?
That's an excellent question. So the equilibrium constant here is just equal to the pressure of CO2. So this tells me that if I have more CO2, my equilibrium constant is going to be greater, right?
Okay, that makes sense.
Yeah, it's weird.
No, it makes sense to me, at least. I got
did that one. So for which reaction does Kp equal Kc? It's a little trickier because there's all kinds of stuff mixed. It's not all gases. We're only looking at the coefficients for the gases. It'd be B. Yeah, tricky. So in this top one, on the left side we have 2 moles of gas, and on the right side we have 1 mole of gas. So that's not the same. The middle one, solids don't count. 3 moles of gas and 3 moles of gas. That's our winner. And down here we have 3 moles of gas on one side and none on the other side. So when you're looking at partial pressures, then the gases matter.